So hello everybody. I'll speak about real-time preprocessing of data for serial-crystallography. So since we are at PSI, and that I'll mainly speak about a PSI detector, well, I think it's a good idea to do that. Well, we've been a lot of people working on this. So basically, we are building the detector system for one beamline, which is managed by Daniel. The project has been supervised by Andy. And in this group of people, we are 3 scientists, I'm not, and 3 engineers, which I'm part of. So Samuel, Alejandro, and I have been doing the coding part. And Nicola, Gianluca, and Shibom have been giving the scientific guidance, let's say, for the work to do. So the outline of the talk is, well, I'll first introduce you serial-crystallography. Unfortunately, nobody did it previously. I'll present you the new ID29 beamline at ESRF. Then we'll speak about image analysis, lossy data compression, peak finding, before drawing some conclusion. So, well, I guess most of you know how serial-crystallography works. So we have X-ray beams arriving here. We have some choppers that generate 10 microsecond pulses with a repetition rate of 1 kilohertz. Then this arrives on a sample, and we have different kind of sample delivery systems. And we can also put laser excitation on them. And then, of course, we need a fast detector, which is a Jungfrau 4M, which has been manufactured here. So this is what the detector looks like. So it's a Jungfrau 4M from PSI with a hook in front of it. And this is the hook as seen by the detector. And this is the back of the detector with really a lot of fiber optics coming out of it. So there are 8 modules, 16 fiber optics running each at 10 gigabit per second output, plus 8 control lines. And this is the data acquisition system we have set up with Samuel and Alejandro. So the frames are directly recorded by the computer, where they are reconstructed. Then we perform pedestal correction and data reduction before doing some bit shuffle LZ4 compression and saving to HDF5 file. And maybe the novelty is that here we have some OpenCL kernels running on the GPU directly inside the computer controlling the acquisition. And we'll focus on this part because that's the one I've done, unfortunately. And for supervising live, we have NanoPixel, which is written by Nicolas Coquel, who's presenting the peak finding in real time with the number of spots as function of time. So when it comes for online data analysis for processing serial-crystallography, well, we can see this as a ladder to the sky. Well, the first thing is being able to dump the data on the disk. And this is something we're not able to do at ESRF. Unfortunately, so image reconstruction, we have seen and we've published with Samuel especially, that we are able to perform this in real time. Then the next step is a veto algorithm, and Philip has done a wonderful work and very clear presentation. So why we should discard most of the frame, probably 90% of the frames. And then we'll focus on intense pixel saving, peak finding. Well, that's what we'll focus on, but the holy grail is being able to perform the indexing at the speed of the acquisition. In our case, it's 1 kilohertz. Okay, here we have the first protein image from the detector. So it's probably lysosym. What we see a beam stop shadow. We see a ring, which is usually attributed to the water, which is disorganized inside the protein. And we see black spots a bit everywhere. So, well, I'm the author of pyFAI, so I'll just come back on some stuff, numerical stuff about pixel intensity correction, then azimuthal integration, because we'll try to use this azimuthal symmetry to guess the background, so which pixels are taken and how they are averaged in order to calculate the mean. And well, we use some accumulators, which simplifies a bit the math. Sorry for all the math. If you don't like, just have a nap for 5 minutes. Then we have one important thing where we calculated the mean, but we need also the uncertainties. And well, pyFAI uses this formula to calculate the standard error of the mean, but this is not what we are interested in, because we are interested in the uncertainties on the pixel value, which is a different one. And the formula is this one. And once again, most people use the Poisson error model, which assumes that the variance of the pixel is the average signal of this pixel. So we have the new accumulators, which are defined here, with the other one which looks like this. And if we look at one image, again, an image taken at PSI. So this was the one used by Detector to advertise for the Pilatus when it came out 12 or 15 years back. We see just few black spots, and this is the azimuthal integrated curve. And I put here the standard error of the mean. So that's the orange curve, and the blue curve, which corresponds to the standard deviation. And well, we still see smooth background, but lots of peaks, and especially on the variance side. One black peak can give here can give a really sharp signal on the diffractive on the azimuthally average signal. So the idea is to use sigma clipping. So if we consider that we have a distribution like this for the pixel in the background, we have some positive and negative outliers, and we basically use the standard deviation to discard them. And we iterate this algorithm several times, and this removes both tails of the distribution. So those are the orange pixels in this graph, and we go from the red curve as a fit to the green curve, which better fits the background. So we have a good approximation of the background. We can perform several iterations. So that's automatic cutoff parameter. Well, this is some results. We see that after 0, 1, 2, 3, 4, 5 cycles of sigma clipping, we have the background that gets smoother. But that's first thing, we're happy. But one problem, we have still positive peaks here and negative peaks. And those negative peaks comes actually from bins that have been completely emptied out. And we have empty bins, and we end up with mean equals 0. It should be not a number, but scientists don't like not a number. And the standard deviation, again, being 0 over 0, again, not a number, but written as 0 to please them. But this completely jeopardizes the results. And this comes from the assumption that we were having a Poisson distribution. It's true that we have a Poisson distribution for the detector is Poissonian, but the ensemble of pixels we are considering are not. Some of them come from black peaks, some come from the background. And just a simple exercise, take 2 pixels, one with a value of 1, one with the value of 99. The mean is 50. And if you assume the Poisson law, both pixels are at 5 sigma, and you have completely emptied the assembly. So the solution is to come back on the definition of variance and take the average, well, the distance of a pixel to the mean, weight it accordingly, and so on and so forth. And we are fortunate to have a single pass implementation that looks like this. And yeah, so this is what it looks like with the Poisson error model. So this is the same picture as previously. And this is the one with the azimuthal error model. And we see that we don't have any negative peaks as previously, and the background is rough, but smooth without positive or negative peaks. That's what we're looking for. The last idea is to take this distribution and to assume that we have Poissonian system, because we have already removed all black peaks. And yeah, that's it. So we spent quite a lot of time in looking at the background, so let's forget about the background and keep all remaining pixels, because those are our pixels. So that's the algorithm of classification we have set up. Record only remaining pixels. The one that we have previously discarded, those are the pixels of interest, and all the other we just measure the background and the standard deviation. And because we know, well, we assume that the remaining distribution is a normal one, we can tune the compression rate that we'd like. The opposite operation is densification. It has been implemented in Fabio almost a year ago, and it's ready. If you have Fabio on your computer, you probably already have it. And so this is a validation case with data coming once again. I think it's an insulin data set that was provided by Detector for advertising the eigenvalue for M. And this is how the background looks like. So we see we have at worst, let's say 1.5 count in the background, and we have the error bars, which are mainly due to the fact that the standard deviation tends to 1 if we assume a Poissonian noise at the end. That's the number of peaks as function of the frame number. So those are some figures. I will not discuss about this because I'm not a crystallographer, and Nicola and Gianluca have, and Shibam as well, have validated that it was correct. We have a 5 times compression in volume with a cutoff at 1 sigma. The compression speed is 250 frames per second running on a GPU, and the decompression speed is 200 frames per second by running on the CPU. And we have the issue of the Poisson model, which adds quite a lot of noise. But once we have this background defined, we can also do peak finding, and this is what we do. Well, basically, it's more or less the same idea as Peak Finder 8, and we implemented this again on GPU using OpenCL. And this is one image that we obtained. So it's the Pilatus 6M image, and I've compared the result coming from Peak Finder 8 interfaced with Honda, or the Peak Finder that I've implemented in pyFAI. And so pyFAI is in green, Honda or Peak Finder 8 is in orange, and we see that for most of the peaks, they fall at the same position. Maybe we have some impression that pyFAI gives more peaks close to the beam center, and that the original Peak Finder 8 gives more points in the outer shell. This is probably due to the fact that I've tuned the two algorithms to give me exactly the same number of peaks. But this is verified, sorry. This is verified. If you look, here is close to the beam center at low Q, pyFAI gives more peaks and it gives less at high Q. Then I've tried to index the data set using CrystFEL, either with the X-Gandalf or the X-Gandalf fast algorithm. And we can see that, well, the indexation rate, the data were already expurged from blank frames, so we should have an indexation rate which is pretty high. And this Peak Finder gives the results that are similar to Peak Finder 8, which was actually found to be the best from the one implemented within CrystFEL. And X-Gandalf fast, well, we see no strong deterioration of the quality of the result with X-Gandalf fast, and the processing time is much faster. So this kind of validates the algorithm when it comes to peak finding. So as a conclusion, we made up a separation algorithm which is able to clean up the background within 3 to 4 milliseconds for a 4 megapixel image. And this is really the performance critical section of the algorithm. This offers us the ability to perform sparse saving of data. And the compression rate can be tuned between 5 times and 100 times. The compression speed is 250 frames per second and occurs on the GPU. The decompression algorithm is already available and the data quality has been validated. When it comes to the peak finder, the results are similar to what has been found with peak finder 8, and the operation speed is 250 frames per second again. And the peak position is validated with CrystFEL. So what comes next? The idea is to have CrystFEL reading directly our new output format. The second thing is that the beamlines enters into production next week. And well, we'll need to have it running at 1 kilohertz, so it will not be for next week. But for this, we will need 4 GPUs in parallel, and to manage to have everything running inside the same computer. So this is the challenge that remains. And here I remind you the different steps, which is image reconstruction, gain correction, pedestal and gain correction, data reduction, saving of so compression, and then redensification of the data. And with this, I'd like to thank you for your attention. Thank you. Graham, of course.
So your spot finding assumes a radially isotropic background.
Absolutely.
If you are using the sampling jet, is that a safe assumption?
Sampling LCP jet, things like that?
Yeah.
That's okay. The only problem we've faced so far is with a certain kind of I think it was Miller sheets or another polymer, where they stretched the polymer to glue it, and by stretching the polymer, they obtain nice parentheses on the image. That was an issue, but now that they are told to avoid stretching the polymer, the shape of the background has no incidence. So, of course, the lower the background, the better, but as long as it's roughly isotropic and we are able to model the anisotropy that comes, for example, polarization is anisotrope, but it's perfectly well modeled, we are able to cope with it, and it's okay.
I think it's very impressive. I mean, if this works.
It's available if you have pyFAI, the latest version. Well, the edges are a bit rough. You can play with it. Well, the challenge remains to have, for now we are using 2 GPUs and we are able to process at 500 frames per second. The next step is putting 2 more GPUs and hoping that the number of interrupts that we have to do will not interfere with the acquisition, because this runs all within a single computer, which is pretty challenging. But yeah, half of the job is done.
There's a question.
For the offline data analysis, do you foresee on-the-fly decompression as part of the analysis, or intermediate right to this? I mean, it is pretty fast,
but what we foresee is, well, for next week for sure, we will decompress the data and look at the data after reconstruction, for sure. But in the until this winter, we hope to be able to have this integrated, the decompression algorithm integrated within CrystFEL, at least one version of CrystFEL, so that we don't need to redensify the data. So it will make the analysis of CrystFEL slower, but that's something we assume, because what we need, I didn't emphasize it at the beginning, but what triggers all that is the first slide. It's this slide. Yeah, the data arrives at 2 times 100 gigabits per second, 2 times 100 gigabits per second, and we have a strong limit at the storage, which is 25 gigabit per second. And you know, our problem is going through this limit.
it's also reading back. You rather invest a bit more CPU time to decompress than store yet again and again. That's why you're integrating in CrystFEL there.
Yes, that's the idea.
And we want to save disk space.
Yeah, and they want to save disk space, but that's their problem. Our problem is the 25 gigabit per second here.
And one thing you didn't mention, you could use this also for vetoing, no?
Yes, absolutely. The algorithm has been designed so that we save all frames, and frames without peaks will not cost much to be saved because we don't expect to have many peaks on them. Pixel to save, to be precise. If we perform both the sparsification and the peak finding, we are able to have a veto algorithm in addition, and we could decide not to save some frames. But we don't expect to win a lot on the storage space by performing the vetoing in real time.
Okay, thanks. Is this urgent? Is it a quick question? Or maybe 2 seconds.
So was it tested against the experiment was crazy?
Yes. Yes, Nicolas did some intensive work, and the anomalous signal gets degraded. We agree. He validated that at 1 sigma, the degradation is low enough that it is able to reconstruct the signal, and the source of the degradation has been identified. Of course, it comes from the heavy atoms, the density of the heavy atoms, and it comes mainly from the peak intensity in the outer shell. And in order to have the data processed with XDS, we have to re-inject some noise, unless XDS is not happy. And one of the problem is that we assume to have a Poissonian noise, and the standard deviation, even at the very high Q, is 1. Yes, it's 1 because it's a photon counter. And the noise we are injecting in the outer layer is overestimated. And because the Jungfrau detector is not an Eiger, it's an integrating detector, not a photon counting one, we should have the variance on the standard deviation that should not be limited by this factor 1. And we hope to have better results. But this is some assumption. But we have investigated the source of the degradation of the anomalous signal and found where it was coming from.
Thank you. We have to stop now. 2-second question, but 5 minutes.
Sorry.